Salam and welcome everyone. So today we're going to be working on the questions on the screen that says calculate the Broglie wavelength of the first question, a mass of 1.0 grams traveling at 1.0 centimeter per second. Then the second question, the same mass traveling at 1000 kilometer per second. And then the third question, a He atom, so helium atom traveling at 1000 meter per second, which is just basically a typical speed at room temperature for helium. That's just more information. Anyways, we're told to solve the de Broglie wavelength of each one of these three scenarios. So the solution for this question, I'm going to start with the first question is for us to determine the de Broglie wavelength. So the de Broglie wavelength, I'm going to have the lambda sign with a sub d because it's de Broglie wavelength of a mass. So the first question of a mass, we have a mass of 1.0 grams traveling at 1.0 centimeter per second. So that is just simply the speed, or you can call it the velocity. So that's just 1.0 centimeter per second. And we're told to determine the de Broglie wavelength. Now, when you're dealing with a question like this and you're looking for how to solve the de Broglie wavelength, the de Broglie wavelength has the formula, the de Broglie wavelength. Okay, so lambda sub d is equal to h divided by p, where h is the Planck's constant. Okay. By the way, this question is from the Atkins Physical Chemistry 11th edition. This is number 13 or question 13 from the subchapter 7a. So this is exercise 7a.13a. So that is the question. So anyways, we have h to be the Planck's constant. So h is also has the value 6.626 times 10 raised to the power of negative 34 joules seconds, while the p is just simply the linear momentum. Now, we are now faced with a question where we're supposed to determine the de Broglie wavelength, but all we know is a Planck's constant because the constant value is basically a constant. It's going to be the same all through. But we also have to notice that we're given the mass as well as the velocity. So if you remember in physics, whether it's high school physics or elementary or general physics in the university, you would note, especially if you're taking physical chemistry or quantum chemistry, you should have learned this in earlier classes. Linear momentum can also be known, or solving for momentum is just simply mass times velocity. So linear momentum is simply mass times velocity. So we can just simply substitute here P for mv. So we're going to rewrite the formula. So the formula for the de Broglie wavelength, so lambda sub d is just simply h divided by mass times v. So here we're going to be able to easily solve for this because from the first question we have our Planck's constant, which is a constant value, we have our mass, and we have our velocity. So we can simply substitute. So now you're going to be wondering, okay, let's just substitute. But we have to remember, and I have to make note of this, and you're not going to know this until you've done enough problems. It's very important when you have a question like this, when you're given multiple units, to make sure that you have the proper units that you need to solve the question. You see, now we have our mass. We're given mass in grams. Then we're given velocity in centimeter per second. And it's only natural for you to be like, yes, I already know what I want to do. I'm just going to simply substitute. But anytime you're given multiple parameters or multiple values in a particular question, make sure you look at the units a little bit more closely because it's possible that you're going to be using the basic units to solve it, or it's possible that you're going to be using the SI unit to solve it. So what this is telling you is that I am not going to substitute 1.0 grams for the mass or 1.0 centimeter per second for the velocity. Instead, I am going to use the SI unit. So now, again, we rewrite the mass that we know to be 1.0 grams. If I want to put this in SI units, it's going to be in kilograms. So that's going to be, mass is going to now be 1.0 times 10 raised to the power of negative 3, because I'm going from grams to kilograms, kilograms. So that is it. Next, we do the same for velocity, and the velocity we're given to be 1.0 centimeter per second. I'm going to turn it from centimeter per second to the actual SI units, which is just meter per second. So velocity becomes 1.0. Remember what centi is? Centi is just times 10 raised to the power of negative 2, then meter per second. So I went from centimeter per second to meter per second, remembering that centi is just times 10 raised to the power of negative 2 meters, right? So yeah, that's it. So now we actually have the value for our mass and we have the value for velocity. Now we have Planck's constant in joule per second. The SI unit for energy is joules, but we need to use the base SI unit. So in case we need to cancel out stuff, we can cancel out stuff. I'm going to substitute the Planck's constant the way it is, and then I'm going to use that to explain the reason why it is so important for you to take care of your units in question. So for example, now going forward, we have the de Broglie wavelength, which is H divided by mv. We're going to substitute. So 6.626 times 10 raised to the power of negative 34 joule seconds. I just want you guys to see something, and then I'm going to explain further. Then you have your mass 1.0 times 10 raised to the power of negative 3 kilograms, okay, times the velocity 1.0 times 10 raised to the power of negative 2 meter per second. So that is it. So that is what you have. Now you can see now we can do anything with joules and we cannot really do anything. Well, the SI unit of energy is joules, but there is also base SI units. So joules, which we know to be the unit of energy, is just simply kilogram meters squared per second squared. So that is the base SI unit or the basic SI unit or the base SI unit for the SI unit joule. So joules is an SI unit of energy, but we also have base SI units where you can break down the SI unit to further um, elementary SI unit value. So basically, the base SI unit for joules is just kilogram meter squared per second squared. And in order for you to be sure what I'm doing is actually right, remember, joules is the unit for energy, and energy is simply force times distance, and force is also mass times acceleration. So really, mass, which has the SI unit of kilograms, acceleration, which has the SI unit of meter per second squared, and distance, which has the SI unit of meters, is going to end up becoming kilogram meter squared per second squared. So basically, energy is the same thing as mass times acceleration times distance. So yeah, knowing this information now, we can just simply substitute wherever joules is, but not forgetting we have joule seconds. So we're just going to substitute kilogram meter square per second square for joules. So you see the reason why units are so important. If we have substituted joules there, if we are left joules just as it is, we're not going to be able to cancel anything out, and then we're going to have a very confusing work. So, anyways, the Broglie wavelength is going to end up becoming 6.626 times 10 raised to the power of negative 34 kilogram meters squared per second squared. And then you have the seconds right here divided by 1.0 times 10 raised to the power of negative 3 kilograms times 1.0 times 10 raised to the power of negative 2 meter per second. So you cancel out the seconds, cancel out the seconds, cancel out the seconds again here, cancel out the seconds, cancel out meter here, and cancel out one of the meters here, cancel out the kilograms, cancel out the kilograms. So what we end up having left is just meters, which makes sense because we want our final answer for the unit of wavelength to be in meters. So anyways, the de Broglie wavelength ends up becoming 6.626 times 10 raised to the power of negative 34 meters divided by, so the denominator 1.0 times 10 raised to the power of negative 3 times 1.0 times 10 raised to the power of negative 2 is just simply 1.0 times 10 raised to the power of negative 5. We can now input this information in our calculator to end up getting the de Broglie wavelength to be 6.626 times 10 raised to the power of negative 29 meters. And of course, we are chemists, so we cannot leave our work in this form because we have to put in the proper number of significant figures. So we have to go back to our question and see what is the lowest number of the sig figs. So we have this one in two sig figs and this in two sig figs. So our final answer has to be in two sig figs. So the de Broglie wavelength is just simply 6.6 times 10 raised to the power of negative 29 meters. So this is basically the answer to the first part of the question. So yeah, I decided to go in detail for this one so that it's easier for you to understand the other ones going forward. Yeah, so we've done that one. So we have the second question where we're dealing with the same mass of 1.0 grams, but at a different velocity of 1000 kilometer per second. So the second question, we have the mass to be 1.0 grams and then the velocity to be 100 kilometer per second. So Now we have mass is equal to 1.0 grams, as well as the velocity is equal to 100 kilometer per second. Let's not forget, we're going to have to convert to SI units. So the mass is just simply going to be 1.0 times 10 raised to the power of negative 3 kilograms, because we're going from grams to kilograms. And then, of course, the velocity is going to be from 100 kilometer per second to the velocity in meter per second. So that's 100 times 10 raised to the power of 3 meter per second, because we're going from kilometer to just meter. So we end up with 100 times 10 to the power of 3 meter per second. So that is what we've done here. So we went from grams to kilograms to kilometer per second to meter per second. So we've done that. And then remember, we have our formula for the de Broglie wavelength to be lambda sub d is equal to h divided by p, which is the same thing as lambda sub d is equals to h divided by mass times velocity. And we know, of course, what our value for h is. H is just 6.626 times 10 raised to the power of negative 34, okay, joule seconds, or 6.626 times 10 raised to the power of negative 34, okay. Remember what joules is again? We know joules to be kilogram meter squared per second squared. And then let's not forget this joules here. So times second. So that is it. So yeah, that is basically it. Yeah. So lambda sub d is just simply 6.626 times 10 raised to the power of negative 34 kilogram meters squared, okay, per second squared, multiplied by seconds, divided by the mass, which is just simply 1.0 times 10 raised to the power of negative 3 kilograms. Alhamdulillah, 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 times the velocity, which is just simply 100 times 10 raised to the power of 3 meter per second. So, of course, we've successfully substituted. So let us start canceling out whatever we need to cancel out. So we cancel out the kilograms, cancel out the kilograms, so cancel out the seconds, cancel out the second, cancel out the second, cancel out the second, cancel out the mass, denominator mass, and cancel out one of the numerator meters. So not mass, sorry, meters. So what we end up having, the only units that we end up having is just simply the meters, which is of course the units for the wavelength. So we have successfully canceled all of the units. Now we can move on to further calculation. So lambda sub d is just 6.626 times 10 to the power of negative 34 meters divided by 1.0 times 10 to the power of negative 3 times 100 times 10 to the power of 3. So this times 10 to the power of negative 3 times 10 to the power of negative 3 here, if you know your math very well, you can just simply cancel it. If it's going to be confusing to you, you can just multiply everything in the denominator on your calculator. But anyways, what you end up here is just divided by 100, right? So you can actually just do this in your denominator on your calculator. So you're going to get 100. So divided by 100. So lambda sub d is just simply going to be 6.626 times 10 raised to the power of negative 36 meters. So lambda sub d is just simply this. But we already know we have to put this in the proper number of significant figures. And the proper number of significant figures is whatever the lowest number of significant figures are in the question. We see that we have 3 sig figs here, but we also have to remember that the mass we're told to be 1.0 grams. So we have to put our work in the proper number of significant figures, which is just simply 2 significant figures. So that would be 6.6 times 10 raised to the power of negative 36 meters. I just realized that I made a mistake with something, but fear not. The mistake I did was in the question where I said is the same mass basically traveling at 1,000 kilometer per second. It is not 1,000, it is 100. So it's 100, please. It's 100. You can see when we're doing the question, when we're doing the solution now, I did it the mass to be 100. In the Atkins Physical Chemistry 11th edition textbook, it is 100. So don't make that mistake. So yeah, I apologize for that mistake. Yeah, I apologize for that mistake. That's not what is in the physical chemistry textbook that we're using in this video. Anyways, so that's it. So that's the second one. The second one, when we did it in two significant figures, we got a wavelength, the Broglie wavelength, to be 6.6 times 10 raised to the power of negative 36 meters. So for the third question, we're told that we have a He atom traveling at 1000 meter per second. So the He atom, and then it was traveling at 1000 meter per second. So we're giving the velocity to be 1000 meter per second. Now you're going to be wondering, well, they didn't give us the mass, but what they did is they gave us the identity of the atom that we're dealing with, and we're dealing with the helium atom. And helium atom has its own mass, and the mass of the helium atom in kilogram is simply 6.64 times 10 raised to the power of negative 27 kilograms. So this is basically the mass of a He atom. So the mass here is this. So we have the mass, we have the velocity, and we can easily determine the de Broglie wavelength for the third question. So the de Broglie wavelength, let's not forget, is just simply h divided by p. So h divided by linear momentum, which can also be h divided by mass times velocity. So we have successfully determined the velocity given to us and the mass, and then we know the Planck's constant, so we can simply substitute. And you see this third question is actually the best one we've had. We have our mass already in kilograms, so we don't need to do any form of calculations or unit conversions. We have our velocity in meter per second, so we don't actually have to convert to SI units. So all we can just simply do is substitute. Now, before we go ahead and do that, we remember that H is simply what? What did I say H was again? H is 6.626 times 10 raised to the power of negative 34 joules seconds, which we can rewrite to be 6.626 times 10 raised to the power of negative 34 kilogram meter squared per second squared. Let's not forget the second, since the full unit is joule second. So times this extra second here. So this is all we need to substitute. So lambda sub d is equal to h divided by mv, which is just simply 6.626 times 10 raised to the power of negative 34 kilogram meter squared per second squared, multiplied by seconds divided by mass, which is just simply 6.64 times 10 raised to the power of negative 27 kilograms times the velocity, which is 1000 meter per second. So 1000 meter per second. So let's cancel stuff out. So we cancel out the denominator meters, and we cancel out the other denominator meters. We cancel out the kilograms. We cancel out the second here. We cancel out the second here. So what we are left with is the actual unit of the wavelength, which is just simply meters. So that would be lambda sub d. Rewriting would just be 6.626 times 10 raised to the power of negative 34 meters divided by 6.64 times 10 raised to the power of negative 27 times 1000 is just 6.64 times 10 raised to the power of negative 27 times 10 raised to the power of 3, which is the same thing as 1000, is just 6.64 times 10 raised to the power of negative 24. So the denominator here is what I got here. So that's that. So now lambda sub d ends up becoming, when you input this whole information here in your calculator, you end up with 9.97892 times 10 raised to the power of negative 11 meters. And again, we are chemists. We have to put our work in the proper number of significant figures. And when we go back to our question, we will see is that besides the fact that this is 1000, we also have to remember that we use He atom, right? And when you go to the question, you see that He atom that we use, the mass of the He atom, we use it in three significant figures. So because that's part of the values that we use in solving this question, we have to use the lowest number of significant figures, which is just three sig figs. So that means our final answer has to be in three sig figs. So we end up having the lambda sub d, so the wavelength, the de Broglie wavelength, to be 9.98 times 10 raised to the power of negative 11 meters, which is just simply the final answer to this question. So we have 9.98 times 10 raised to the power of negative 11. So, yeah, that's just basically the end of the video. But I want to quickly mention something that if you have any suggestions, concerns, or questions, please put it in the comment section. I am here to help you guys and also share with your classmates. If you would like to send me materials that you would like me to work on the channel, maybe like class notes and exercises, you can feel free to do so and send it to my email at shuhabitutoring@gmail.com. I also wanted to mention that if you're a student who's trying to succeed in any of your STEM related courses, whether you're in middle school, high school, or college, I am the tutor for you. I help students succeed in all your STEM related courses by my way of tutoring and mentorship. And if you love my teaching style, please email me at yohabitutoring@gmail.com because I am a great tutor and mentor and I'm here to assist you to the best of my capability. So I wish you guys all the very best. Thank you for spending time with me. Assalamu alaikum wa rahmatullahi wa barakatuh.